This talk is about using device tree overlays on top of PCI in order to support complex PCI board. But before diving into the topic, let me give you some few words about me. I am an embedded engineer at Bootlin. I contributed to the Microchip LAN966x PCI driver, received the first driver using the feature, the device tree overlay feature on top of PCI. This driver has been upstream, of course, and I am living in Toulouse, in south of France. So what is the use case handled by this feature? The LAN966 PCI device, in fact, we give you some details in a few slides, but I know also about the FPGA from Alveo. This one exposes several controllers, DMA, UARTs on PCI bars, and those controllers have the driver already available upstream and used on other devices. This is a little bit the same for ASICS 9100 with GPIO or SQRC SPI buses. I know also about the RP1, the RP1 PCI board, which is currently upstreaming. I mean, the series is under review. And a few years ago, in 2023, Rob Ring talked about this feature at Plumbers, and the name was non-discoverable device on PCI. So let's have a look at the LAN966 chip itself, just to really understand what the feature is. So Microchip proposed this chip in two modes. The first one is the traditional SoC, which is already supported with all drivers available, and everything's working. And the second one is in PCI device. This is our use case. So in traditional SoC, we have the internal CPU cores with a bunch of peripherals as usual, and everything is defined with a device tree, in this case, the LAN966x DTSI. Just extract this device, DTSI, nothing strange in that. There is a SoC node with a bunch of devices under that node. In PCI device mode, in fact, Microchip removed the CPU cores from the SoC and replaced them by a PCI endpoint. So in this mode, peripheral access is by the PCI root complex, in fact, your own PC. They are memory mapped through PCI bars, so they are memory mapped I/O devices, and interrupts are routed to the PCI ENTX interrupts. Other than that, it is exactly the same set of peripherals. So all drivers existing for the SoC should be reused. This device is a PCI device, so I need a PCI driver in order to have my driver loaded when the PCI infrastructure detected that the PCI device is connected. I mean, we need to match the PCI vendor ID and device ID. But, well, how to instantiate the other drivers needed for the bunch of peripherals from the LAN966 PCI driver? We're going at this instantiation. So the driver, as I already said, are used in the SoC. So they're based on a device tree description. On our side, we don't want to reinvent the wheel. We don't want to modify existing driver to adapt them in our case. And we don't want to have a massive description of interconnection or dependency between drivers directly in C code in our driver. So what makes sense is to use a device tree overlay. So a device tree overlay is just a device tree description, but applied at runtime. So with an overlay, we can add or remove properties when it is it is applied, and of course, perform the revert operation when we move. And one more thing, an overlay can be applied to a specific node in device tree. So, side by side, there is the description for the SoC, the LAN966x PCI, and the overlay I used at the end in the driver. So we can have this. We can see that we have the exact same node for the switch node, for the reset node, for the GPIO controller node. So that sounds pretty good. Same hardware, exactly same description. But we need to attach the overlay. I said we can attach the overlay on a specific device tree node. But, well, there is no device tree node related to PCI. Where are we going to attach the overlay? In fact, PCI devices are discovered during runtime. There is an enumeration, and it is really dependent on the topology. I mean, on board or furthermore, you can add a PCI board on a slot, which a bridge inside, and it can give other slots. So it is really dependent on the system. And in the base device tree, in fact, we have only the PCI root bridge. Well, let's have a look at the enumeration itself. From a PCI root bridge, well, really simplified, but from a PCI root bridge, we look at devices. If we find a device, we create the struct PCI device, we compute and assign resources, and if it is a bridge, we are going to look at the buses behind the bridge. If it's a device, okay, everything is done. We look at the next device. And this leads to this representation internally. So we have the base description, and thanks to the PCI enumeration, we have the bridges and devices that appear. And of course, no device tree related to those items. The idea was to create a runtime device tree node just after computing and assigning the resources. In fact, node that creates and properties in node are set based on the resource computed during the enumeration. With that done, our representation is the following. In fact, several data nodes were created at runtime and attached to the device itself, PCI bridge and device, and to the parent node in the device tree. So this is available since kernel 6.6, enabled by config PCI dynamic OF. And it is done by PCI OF PCI make dev node. It is a really direct call for bridges, and we use a final fix-up for device, just to avoid the creation for all possible devices in the world, but just for known devices that use this feature. And as I said, we attach on the DT node and on the strict device representing the device itself. Just a few words about interesting device tree properties. One for address translation, the other one for related to interrupts. But let's have a look at ranges. So we can have a simple translation using the ranges property. Ranges is composed of several items. On each item, we have a child bus address and the parent bus address. And the goal is to translate from the child address space to the parent address space. So the first step is to find a matching item. The matching item from when you have the child address is the one where the child address is in the range. Once found, we can compute the offset from the base to the child address, and we apply the offset on top of parent base value in order to have the translated address. There is a second kind of translation, in fact, well, pretty similar but distinct, is the PCI translation. In that case, in the child port definition, we have some flags that appears, and it is used only when device type equals PCI. Those flags define the kind of area used by the address. Quite a lot of value, but for the translation, only the space code is used. So we can define config space, IO space, and the memory space, either 32 or 64 bits. So in the PCI translation, we have to find a matching item to have both rules true. The first one, the flags need to match, and as previously, the address should be has to be in the range value item. If it match, as before, we compute the offset and apply it on top of the parent base in order to have the translated address. So these properties on PCI host bridge, we perform a PCI translation in order to translate from PCI addresses to host bus address. On bridge, it is also a PCI translation, and we translate from the secondary bus addresses to the primary one. On PCI device, it is just a simple translation, and we translate from PCI base address register to PCI addresses. And in the overlay, in the end, it is also a simple translation, but we translate from the internal chip addresses to the base address properties. Give you this example, and from the reset controller, for instance, at the bottom of the example, we have the range value. This one is translated thanks to the ranges at the parent node, the endpoint bus, and we translate from the chip internal address to the base address register. Once level up, we have the device, PCI device itself, and we have the translation from PCI base address to PCI addresses. One more level, a bridge, one more level again, the PCI host controller. So based on that, we have all the translation performed from the physical register value inside the chip E200400C to an address that can be used by the CPU in order to access the register through the PCI. A little bit on interrupt right now. We need to also describe interrupt at some point. The first idea was to use an interrupt map property in order to remap interrupts. And in these properties, we need a P handle to the parent interrupt controller. I mean the ampersand open peak, for instance. This P handle is not always available. I mean, on a CPI, it's quite complicated to have a P handle pointed to the interrupt controller. So we decided to not use the interrupt map controller, but consider the PCI device itself as an interrupt controller. This is available since kernel 6.11. For instance, here the switch needs the interrupts 9 and 12 from the OEC. So we can see that it is a traditional description with interrupts parents. So nothing strange in that. But on the OEC, for instance, this is an interrupt controller available on the chip itself. and it is connected to the PCI ENTX. So it uses the interrupt number 0, right? But there is no interrupt parent definition in the OEC node. So the OF core, when it resolves this interrupt mapping, works up to the parent node until an interrupt controller in file. Well, an interrupt controller or interrupt map. In our case, an interrupt controller. So it goes up to the PCI device and consider it as an interrupt controller. So it is the responsibility for the PCI device driver to route the interrupt 0, I would say, used by the OEC controller to the PCI ENTX. The device tree properties added to the node at the end are for bridges: the compatible range, PCI, address cells, and size cells, and ranges as described. And for device compatible, address cells, size cells, ranges as described, and the interrupt controller in order to handle correctly interrupts. I'll talk about ACPA. What can be done on ACPI? Well, on x86 there is an ACPI, there is no device tree, so our internal representation is based on ACPI description. With the enumeration we have the device, and that's all. Well, not in fact. There is device tree, at least can be used in x86. And what is done is at boot there is an empty device tree node created. But we can enable our config PCI dynamic OF node in order to create all the missing nodes, as we did on device tree-based system. But there is one missing node, the PCI root bus. I mean, the created node needs to be attached somewhere, but where is the somewhere? Well, we already create a bunch of nodes, so we create just one more. And this is done when the host bridge registers. With that done, with the exact same representation, so exact same scenario on device tree-based system and ACPI. The host bridge creation is done by OFPCI make host bridge node, called during the bridge registration. Several properties are added. The nodes are attached to the device tree node, to devices, and we have to be careful because the parent node of this node is the root node, and the root node is handled by platform bus. So when at runtime we add a new node on the node handled by the platform bus, a device is created. In our case, we already have the device. It's the PCI host controller itself. So we just take care of disabling, in that case, the device creation from the platform bus in order to avoid the device duplication issue. In terms of properties, nothing really different compared to bridges. Device type PCI, address cells, size cells, ranges. So the last things we need in order to have everything working is the LAN PCI driver itself. Right? The driver that match the vendor ID and device ID of our device. So I said before, we need to handle the interrupt. So we dedicate one hierarchical domain. We have only one interrupt in this domain, in our case the ENTX. And we forward the ENTX interrupt to the interrupt domain. That's all the codes that do that. I wrote the in a driver or LAN966x agnostic way. I mean, if other drivers in the future want to use this code, you need just to copy-paste in a shared file, and both drivers can use the exact same code. We need the overlay, so the overlay is compiled, it is embedded in our module, we retrieve the overlay, and thanks to OF overlay FDT apply, we apply the overlay at the specific node, the dev OF node, which was created during the PCI enumeration. So the probe, and all this driver is available since 6.13, we create the interrupter controller, we load the overlay, and we populate platform devices thanks to OF platform populate. So the big picture, so starting from the base description, either on device 3 or on ACPI with the node creation on ACP in the ACPI case, all the nodes created during the PCI enumeration, and at the end, specific to the driver itself, the overlay and its loading, the IRQ domain handling, and the device attached as the PCI device child by OF platform populate. A few words about specific drivers, the system issues we faced on in this during this topic. Most of them are due to the fact that everything used and reused was designed for the SoC use case. I mean, quite a lot of drivers was designed to be built-in, designed to have only one instantiation at boot time, and with our case, we need them to be built as modules, and we need to support insertions and removals. So, ref counting issues, register component list issues. I mean, when we registered, we had the device on a list, but never removed from the list when we unregister. So you can imagine one of my colleagues would say, choc à pic. The memory leak issues, some dependency issues, race condition issues, this kind of stuff, and on several components, and I don't want to blame any component, but you can see that this core component, syscon, reset, clocks, interrupts. I still have some pending with firmware devlink. I have a series currently discussing upstream. Detected some on I2C, I2C Max. And in all cases, we take the issue one by one, try to observe what happened, to fix, pop of the fix upstream, and so on. Today, the driver is working upstream with the nodes defined in the device 3 also available upstream. I really wanted to thank some people. First, Criminology is starting this work, explored several ways, to the basis. Then Lizzie who's introduced the PCI device and bridges node creation, node create during the enumeration, and also I will thank maintainers on several systems and subsystems for reviewing, discussing, asking for improvement, and more, many more. Thanks. Any questions? Yeah?
Is there a mic?
I don't think so.
In your example, as far as I've understood, you're using classical PCI interrupts. Do you have experience with message signal interrupts?
Yeah, we have something with the MSI. The MSI, in fact, is used by the Raspberry. At the beginning, I said that the Raspberry model is going to be upstream and use exactly the same stuff as the LAN966 PCI driver. So in my use case, LAN966 PCI driver, I have only ENTX, right? But code is available for the Raspberry Pi, not merged yet, but in a good way, in good shape to be merged. So the MSI, in fact, have to be handled by the PCI driver. You have to create an interrupt domain, and you have the MSI instead of ENTX. All the other part, I mean, from the users inside the overlay requesting an interrupt, it's just a number. MSI or not MSI, it's exactly the same. Other question? Okay, thank you all for attending.